Today we're going to talk about forces and some other stuff. So here's what a force is. A force is a push or a pull. It acts on an object and requires an agent. That means one object must exert a force on another object. Objects experience forces, and forces are exerted by objects. Force is a vector, so it has magnitude and direction. The magnitude of force is measured in newtons, which a newton is equivalent to 1 kilogram meter per second squared. And there are contact forces in which the object exerting the force is touching the object experiencing the force, or there are long-range forces where they're not touching. For example, Earth exerts a gravitational pull on a skydiver, but the skydiver and the Earth are not touching each other. So that's a long-range force. Here are some examples of forces that we're going to be seeing this year. Number one is the weight force, which is the gravitational pull of the Earth on objects near Earth's surface, or any other planet for that matter. The weight has a symbol F subscript G. Sometimes people call it force of gravity. Sometimes people call it weight. Those are the same thing. Its magnitude is equivalent to the mass times gravitational acceleration. On Earth, gravitational acceleration has a magnitude of 9.8 meters per second squared, and it always has a direction of down. So since gravitational acceleration is always down, gravitational force is always down. It is not the same as mass. People often mistake weight and mass. Those are not the same. Weight is a force. Another common force is the spring force. The magnitude of the spring force is K times delta X. K is the spring constant of the spring. It's different for every spring, depends on how strong it is. The spring inside of the suspension of your car has a much larger K value, which is measured in newtons per meter. It's like how many newtons it takes to stretch it or compress it by 1 meter. So the one in your car is suspension is a much higher K value than the spring in your ballpoint pen. This negative sign should be here printed in the slide, but it's not. I had to draw it in. This is because the direction that of the force exerted by the spring is opposite the direction that it's displaced. This factor here is how far the spring is displaced from its equilibrium position. So if I compress this spring to the left, like its equilibrium position is here, and if I compress it to the left, then it's going to force that box back to the right, opposite the direction of the spring's displacement. Or this spring has been stretched to the right beyond its equilibrium position, so it is going to force that box to the left. It's like glued onto the box there. So the spring force is opposite the direction of the displacement of the spring from its equilibrium position. Another common force is the tension force, which is exerted by ropes and chains and strings and stuff like that. Has a symbol F subscript capital T, tension force. It is always directed towards the rope. In other words, ropes can't push things, they can only pull things. Another common force is the normal force. Normal in this case does not mean ordinary. Normal in this case comes from the math definition of the word normal, which means perpendicular. And that's because the normal force is always perpendicular to the surface. Normal force is a force exerted on an object by a surface, and it's always perpendicular to the surface. So in the case on the left, we've got a level surface. It's horizontal, So the normal force will be perpendicular to that surface, which is just straight up. But in this example over here, we have a surface that is inclined. And so the normal force will be perpendicular to that surface this way. Another common force is the friction force. The friction force is exerted by a surface on another surface. It's a retarding force. It always slows down the object. It can never speed it up relative to the object exerting the friction force. Here's the magnitude of friction force. Friction force is equivalent to this factor called mu. This is the Greek letter mu, and it stands for the coefficient of friction, which depends on the stickiness of the two surfaces that are rubbing together. And you can look those values up, or they'll be given to you. The other factor that determines magnitude of the friction force is the normal force. Like, how hard are these two surfaces being pressed into one another? The direction of the friction force is always parallel to the surface, and it's always in the direction opposing motion relative to each other. You see two different mu values between every two surfaces. One is called static friction, where the surfaces are at rest relative to each other. The other is kinetic friction, where the surfaces are moving relative to each other. So if you're going to look up the coefficient of friction between, I don't know, steel and wood, then the table would have two values. It would have one for when they're at rest relative to each other, mu static, and it would have another for when they're in motion relative to each other, mu kinetic. And you would have to know which one to use depending on whether they're at rest relative to each other or moving relative to each other. The kinetic one is always less. It's easier to keep the object going once it's already going. Here's another force, drag force. It acts similarly to friction. It's sometimes called air resistance, in that it's always in the direction opposing motion. It's a retarding force. But friction force depended on the value of the normal force. In this case, there is no normal force. There is no surfaces involved. The magnitude of the air resistance force, the drag force, depends on the velocity of the object as it's traveling through the air. Sometimes it depends on the square of the velocity. In problems involving air resistance, you'll be told what the function is. And there's this other relevant phenomenon called terminal velocity, but we'll talk about that later once we've seen Newton's laws. Here's several forces that might pop up, but are going to be less common than the ones we've already discussed. Okay, before we start applying forces and learning about Newton's laws, I want to discuss systems. So, a system is a portion of the universe chosen for analysis. In other words, it's a collection of objects that you have chosen to call the system. Now, on the other hand, the environment is everything else in the universe that you have not chosen to be in the system. So the universe consists of everything in the system and everything outside the system. Everything outside the system is called the environment. Sometimes objects within the system will exert forces on other objects within the system. Those are called internal forces. External forces are when the environment exerts a force on the system. And the key thing about systems is you get to choose what you're considering to be the system. It's purely a mental thing. So whenever it suits you, you can choose, I want this, this, and this to be in the system. And then all of the forces that exist between those objects are internal. And then halfway through the question, you can decide, I need to consider a new system. And you can redefine what the system is. We're also going to talk about center of mass. The center of mass is a point, a location in space. It's a weighted average of the mass of every particle of your system. So the center of mass of your system is like exactly in the middle of your mass distribution of the system. And here's how it's calculated. To find the the horizontal position of the center of mass, you'll use this formula. This is the Greek letter sigma. It stands for doing a summation. So for every particle in your system, you'll take its mass, multiply it by its position, and then you'll add up all of those. So if your system has 3 particles in it, then you'll have mass of particle 1 times position of particle 1 plus mass of particle 2 times position of particle 2 plus mass of particle 3 times position of particle 3. And then you'll divide that whole thing by the sum of the masses. So mass 1 plus mass 2 plus mass 3. And that will give you the horizontal position of the center of mass of your system. Here's a more detailed explanation of how to calculate both the horizontal position of the center of mass and also the vertical position of the center of mass. The only difference is you replace all of these horizontal positions in your equation with vertical positions in your equation. So if you have a 2-dimensional object, you'd have to calculate both the horizontal position of the center of mass and the vertical position of the center of mass. First, we'll do a 1-dimensional object. So my system here consists of two particles. 1, 2. All right, so I would like you to pause the video here and attempt to calculate the position of the center of mass of this system. Okay, so to do this, we're going to use the formula. The horizontal center of mass position equals the sum of the mass of each particle. I is just a little index letter we use, times the position of that particle, and you'll do the sum of all of those for every particle in your system, divided by the sum of all of the masses. And then sometimes on sigma notation, you go from I equals 0 up to I equals, in this case, it would be 2, because there's 2 particles in our system. All right, so filling in our numbers, the position or the mass of the first particle is 10 kilograms. The position of the first particle is 0 meters, plus the mass of the second particle times its position, 5 kilograms times 1 meter, divided by the sum of the masses, 10 kg plus 5 kg, which comes out to 0.333 meters. Kilograms will cancel out of the numerator and denominator, and we'll be left with meters. All right. Now we're going to try it with a 2-dimensional object. This 2-dimensional object is made up of 3 particles. 1 particle, 2 particles, 3 particles. These little connector things have no mass. This little connector thing and this little connector thing. They're massless, so we don't have to worry about them. Only got to worry about these 3 particles. So I want you to pause the video again and try and calculate both the horizontal position of the center of mass of this system and the vertical position of the center of mass of this system. Okay, I think we're ready to unpause. So I'm going to need to do the following. I will need the formula. I have 3 particles, so I'm going to have to do mass of particle 1 times position of particle 1 plus mass of particle 2 times position of particle 2 plus mass of particle 3 times position of particle 3 divided by the sum of the masses. And that will give me the horizontal position of the center of mass. And then I'll have to do the same thing to get the vertical position of the center of mass. But I can like eyeball it that the center of mass of this system is going to be at a vertical position of 0. But I don't want you to just take that for granted. So we'll actually do the calculation. So I'm going to replace all these x's with y's. And that's the formula to get the vertical position of the center of mass. All right. So I have all the masses, but I don't have all the positions. All I've got are these angles. So I'm going to have to do a little bit of trig here. So I have to imagine this triangle. It's a right triangle. The length of the hypotenuse is 96 picometers, and the angle there is 52.25 degrees. So this horizontal position is going to be 96 cosine 52.25 degrees, and this vertical position is going to be 96 sine 52.25 degrees. I'll punch both of those into the calculator. And I have 58.77 picometers and 75.91 picometers. All right, I can draw a similar triangle down here to get the position for this other particle, but it's basically just a mirror image. So this one will have a horizontal position as well of 58.77 picometers and a vertical position of negative 75.91 picometers. So that's its position. Now I can plug everything in. This big particle here just has a position of 0, 0. It's right on the origin. Its center of mass is right on the origin here. Right there. All right. Plug and chug time. Okay, mass 1, 16 units, position 0. Particle 2, 1 unit, horizontal position 75.91 picometers. Particle 3, 1 unit of mass, 75.91 picometers. Divide the whole thing by the whole mass, 16 units plus 1 unit plus 1 unit. Punching it into the calculator gives me 8.43 picometers. That little mass unit is going to cancel out of the numerator and denominator. All right, now doing the vertical, I've got 16 units times its vertical position of 0. I've got particle 2 has 1 unit of mass and a vertical position of positive. Oh, shoot. I realize that I have made a mistake. I accidentally plugged in the vertical positions here and here instead of the horizontal positions. So that's wrong. Sorry about that. The horizontal positions of those were 58.77 and 58.77. Punching that into the calculator, 6.53 picometers. Okay. Particle 2's vertical position was 7591 picometers. Particle 3 had a mass of 1 unit and a vertical position of negative 75.91 picometers. And I'll divide that by the sum of the masses of the 3 particles, which is 16 units plus 1 unit plus 1 unit, which totals to 0. So the center of mass of the system is located at 6.53 picometers, comma 0. Okay. Yep. All right. So that one was two-dimensional, but the vertical center position of the center of mass was pretty obviously 0. Like it was a symmetrical object. Here's a two-dimensional one where it's not symmetrical. And you have to find the center of mass of this. Now I'll give you one hint. Consider it as 2 particles, one of which has a center of mass right here. This is the symbol for center of mass, by the way. And the other has a center of mass right here, right in the middle of it. This thing is uniform, which means the center of mass will be right in the middle. You could have things that don't have uniform density, but this has uniform density, so the center of mass is right in the middle. So consider this as a system of 2 particles and see if you can calculate the position of the center of mass. One other hint, since this is uniform density, the mass of each particle will be proportional to the area of each particle. Pause the video, take a crack at it. All right, here's how this is done. First, I got to find the position of the center of mass of each thing, and I also got to find the area, which gives me the relative mass of each particle. So particle 1, its center of mass is at a position of 0.4 meters, 0.40 meters, comma 0.20 meters. Like it's exactly here, which is 0.4, and it's exactly here, which is 0.2. This one up here, it has a center of mass there, which means this is 0.10, and this is 0.10. So if I drew this all the way down, this thing has a horizontal position of 0.70 meters because it's 0.10 from the end, and the whole thing is 0.80 meters long. As for the vertical position, that would be here, which is going to be 0.4 plus this amount, which again is 0.10 because it's half of this 0.20. So if this is 0.10, then this position here is 0.50 meters. So I now have the position of this center of mass as 0.70 meters horizontal and 0.50 meters vertical. All right. The area of this one, which is proportional to the mass. Maybe I should switch the order there. The mass of this guy, which is proportional to the area, and the area equals 0.4 times 0.8, 0.32 square meters. And this smaller one is 0.2 times 0.2 is 0.04. 0.04 square meters. All right, time to start plugging into the formula. So to find the horizontal position of the center of mass, I'm going to do the mass of particle 1, which is 0.32 meters squared. That's actually the area, but since the density of all these is the same, I'm just going to do it as area. 0.32 meters squared times its horizontal position of 0.40 meters plus particle 2, 0.04 times 0.7 divided by the mass, the sum of the masses. And as you can see, all of the meters squareds cancel out of the numerator and denominator. So it didn't matter that I was in this area thing instead of mass. And punch that into a calculator is 0.433 meters. And then I'll do the same thing, but with the vertical positions. So the vertical position of the center of mass is going to be 0.32 square meters times the vertical position, which was 0.2, plus the other mass, 0.04 square meters times its vertical position, which was 0.50 meters. I'm getting that from right here. Divided by the sum of the masses. 0.32 meters squared plus 0.04 meters squared. Punching that into the calculator gives me 0.233. So the center of mass has a position of 0.433 meters, comma 0.233 meters. So if I was going to draw that on the diagram, that would be around here. Looks about right. It will certainly be somewhere on this line adjoining the two. It's pretty simple when you have a system of only two particles. And it'll be much closer to the big particle's center of mass because it's weighted by mass. And that's where we're going to stop for today.